Hello everyone. Welcome to my keynote today. So today I'm going to talk about semantic communication for media compression and transmission in next generation communication networks. Those who don't know me, my name is Professor Anil Fernando from the Computer and Information Sciences Department at the University of Strathclyde in Glasgow, UK. So I'm mainly working on video processing and communication. So before we start the presentation, let me give an short introduction to my research domain. I'm mainly working on semantic communication, different aspects of semantic extraction, how semantics can be used for different applications, mainly for like media communication and processing. Apart from that, also I'm working on video coding, energy uh, using machine learning and AI concepts, and how energy can be further optimized for different networks and power networks and so on. And also I'm working on emerging technology on compression and transmission for IoTs and IoVT and the other domain. Mainly I'm working on quantum communications and neuromorphic computing and IoT for media applications. And these are some of the people that are working in my domain on semantic communication, which is the focus for today's presentation. So let me give you an introduction to the semantic communication, the basic concepts of semantic communication. So those who do not know anything about semantic communication, they can think about how they can apply for different applications based on the concept of semantic communications. So most of you have heard about Shannon, who is considered as the father of information theory and present communication systems. And he published an article on mathematical theory of communications in 1948, which has laid the foundation for the present day's digital communication that we are experiencing today. Not only today, like for the last 7 decades, everything was depending on what he proposed in 1948. So basically, he broke down the communication process into three fundamental levels. We call level A, level B, and level C, where level A is mainly talking about the technical problem, how accurately the information or the symbols can be transmitted between two locations. And in level B, he proposed this as a semantic problem. How precisely do the transmitted signals convey the desired meaning at the receiving side? And level C, which was talking about the effectiveness problem. How effectively does the received meaning affect conduct in the desired way at the receiving point? So what is level A, the technical problem? How accurately can the symbols of communication can be transmitted, defined as level A? So the goal is to faithful reproduction of a message from a sender to the receiver. It's not considered the meaning of the message or the semantics of the message. The action or the impact of the message that causes at the receiving end is also not the concern in level A. So it is basically concerned with the physical transmission of symbols, bits, letters, or signals. So accuracy, precision, and efficiency of the channel is the main concern. And overcoming physical limitations like noise, distortion, and bandwidth is the other concern. So the analogy is your goal is to ensure a sealed letter arrives with the exact same words written on it without caring what those words means at the receiving point. So what are the key concepts and Shannon where we model? The model focused on level A, information source creates the information, for example, from a microphone or from a camera. The transmitter encodes the message into a signal. So for example, it's microphone or modem. So the channel is the medium that carries the signal. That can be copper wire, fiber optic, or wireless channel. Noise source, any which is considered as the enemy of the level A. Anything that distorts the signal, example, static noise, typos, and sunspots, and so on, are considered as the noise source. As the receiver, decodes the signal back into the message, example, a speaker or a computer model. So destination, the person thing that receives the message and taken care of by at the receiver to digest the message and take some actions. Success at level A is measured by the fidelity of the signal the signal at the receiving station destination compared to the source, which is considered by different quality metrics. So modern example of level is all about bits and signals I told you. It's Wi-Fi network routing, ensuring the packets are sent and received without corruption. The router doesn't care if the packet is part of a cat video or a bank transfer. So the storage device is also not considering what is inside the file. It's writing a file of ones and zeros to a disk and reading them back exactly. The hard drive doesn't know exactly what exactly it was in the message. SMS has the same property. So therefore, in essence, level A is the engineering layer that makes all modern digital communications possible. So why level A matters? The indispensable foundation, a prerequisite for higher levels. You cannot solve level B or level C without level A. So drives the innovation. Challenge of solving level A problems lead to error detection and correction. Example CRC, Reed Solomon, and Holocaust, and so on. The data compression algorithms, efficient modulation schemes. Example 5G, and so on. Universal framework. So that's the most important thing is provide a mathematical way to measure the information bits and the capacity of a channel applicable to any communication system. So conventional communication system building on level A is solving the technical problem of the level A problem leads to solving the semantic problem of level B and effectiveness problem in level C. So with that in mind, so we can consider the conventional communication system that we had been experiencing for the last 7.5 decades. So we have the source, information source encoder encodes the information which exploits the correlation between the information and compresses. And then we have the channel decoder. The job of the channel decoder is to provide some kind of additional bits to protect the data and then followed by the modulation and send it to the channel. The channel will add some channel noise at the receiving end. We demodulate the signal and channel decode it and then source decode it and send it to the destination for the reproduction of the information. That considered as the like a simple end-to-end classical communication system. So the most important part is the channel. So channel can carry only a limited amount of information at a time. So we define this as channel capacity in conventional communication system. So it is basically governed by the channel's capacity theorem, provides condition for solving the technical problem, where C is the channel capacity and B is the bandwidth available for the data transmission log 2 to the base 1 plus signal to noise ratio OS over N, where H is defined as a signal power and is the total channel noise power across the bandwidth B. So now our objective is to maximize the channel capacity for a given net channel, coaxial cable or wireless channel. And B is the bandwidth. Bandwidth cannot be changed because for a given cable, the bandwidth is fixed. And the other parameter that we can control is the signal power, and noise power is also quite constrained depending on the channel that we use. So by changing the B and S, we can change the channel capacity. So there is a maximum limit that we can go for B and S. So therefore, the channel capacity is a limited amount of resource for a given channel. So increase the channel capacity, like I told you before, it can increase the signal power, increase the channel bandwidth, decrease in the noise, and therefore the channel's limit, he has defined the limit is EB over N naught minus 1.6 dB. So beyond that, we cannot design any modulation or error correction codes that will taken care of by the channel. So therefore, we are reaching the maximum capacity of the channel in present days technology, which is driven by the motivation for level B communication consideration in the last few years. So the limitation of traditional communication is a channels model is a brilliant foundation for the present day communication system. The focus is the faithful transmission of symbols or bits between two endpoints, and the goal is to maximize technical accuracy. Did the receiver get the exact bits that we wanted to send? So blind to the meaning, the network doesn't care if the bits are from source A or source B or vice versa. The problem is the inefficient for a world of smart devices and AI. Sending vast amount of data just to convey a simple meaning is wasteful. So the network is a dumb pipe for the time being. So, what is the semantic communication? The core idea is the successful transmission of meaning or intent rather than considering the bit level information. So, the goal is to ensure the receiver understands the message significance. So, did the receiver comprehend what was intended for the transmission? And the key difference is it considers the purpose of the message and the context of the communicating agents rather than the bit level information. So, therefore, we can define the semantic communication as an end-to-end process designed to transmit and receive meaning effectively, efficiently using shared knowledge and reasoning to send only the most critical information. So how it works, we will look into that. Semantic communication loop is an intelligence at both ends. Semantic encoder analyzes the source data, extract its meaningful features based on a shared knowledge basis. So we'll come back to that shared knowledge base later on. So it decides what is necessary to send. So the channel transmits this compressed semantic information. Semantic decoder job is to interpret the received signal, uses the same shared knowledge base to reconstruct the original agent intent or generate a meaningful response. It is a collaborative process of interference, not just blind transmission. So let's consider an example here. So in traditional communication, if I want to send this information across, the high temperature today will be 28 degrees with a 10% chance of precipitation and winds from south at 5 miles per hour. So which needs approximately about 100 bytes of data. The receiver must process this to understand it. Now, coming back to semantic communication, we extract the meaning of this sentence. Okay, by extracting this meaning, it is clear that so it will be a nice day today. So if that information is sent to the receiver understand what exactly the transmitter wants to send to the receiver. So which is basically only needs approximately 20 bytes. The receiver with a shared understanding of nice day means warm, sunny, and calm, understand the complete meaning. So therefore, by sharing that shared knowledge between the transmitter and receiver, we can reduce the channel bandwidth by 80% compared to the original information. So therefore, semantic communication is massively more efficient than the traditional communication. So why it matters? The benefit is unlocking the next generation of technology. It's radical efficiency, drastically reduce the amount of data that needs to be transmitted, saving bandwidth and energy. Enhanced reliability, even if some data is lost or corrupted, the core meaning can often be recovered using the context. So true machine-to-machine interaction is essential for the IoT, autonomous vehicles, and the metaverse, where machines need to understand each other's goals and states. So circumventing channel's limit pushes the frontier beyond the classical capacity of a channel by measuring the performance in semantic bits or task success instead of raw bit accuracy, which will eventually increase the channel capacity or the virtual channel capacity. So semantic communication can solve the semantic problem alone and can enable the solving of the effectiveness problem in level C. So far our focus is not level C, so therefore I'm not going to talk too much about level C. So basically, this is also same thing that level B, if we solve the level B and level C will be the next. So we are not going to touch about the level C. For example, classical example is now consider this one. A drone receives a corrupted command, right? You can see that MOV3NOR7H instead of move north. So if its semantic engine can infer the intended meaning from the context of the mission, and the corrupted bits can still execute the correct action so that the drone can be maneuvered to the north. So you can understand how powerful the level B and level C communication can be, provided that the meaning has been sent to the receiver and they take the necessary action which the transmitter intended to the receiver. So these are some simple examples how semantic communication can be useful is for image transmission. Look at the first column, which is the original image, and the same middle column is the semantic feature extraction from the image, and we call the semantic map, which is the one that is sent to the receiver, and the receiver can regenerate some of the information from the semantic map. You can see the correlation between the first column and the third column. They are highly correlated. The semantic meaning has been transmitted to the receiver with much less bandwidth. So let's consider a simple example, channel capacity in communication. So semantic communication scenario is a user sends a voice data for a virtual assistant to understand the command. Can you play some jazz music? In traditional communication, raw audio for 5 seconds multiplied by 16 kilohertz, which is the sampling rate, and 16-bit PCM, which needs about 1.28 million bits for capturing this information. And channel capacity, we assume 512 kilobits per second, and we can calculate the time required by taking the ratio between 1.2 million bits divided by 512 kilobits per second, and which is about 2.5 seconds approximately. Now look at the same thing that is based on semantic communication, transmit only the intent and the slot values, which we need 10 bits for the slot and 10 bits for the intent, and error correction and metadata. If you assume we need 100 bits, total to 120 bits, and transmission time is like 120 divided by 512 kilobits per second, which is about approximately about 234 microseconds, which is the fraction of the original time that is required with the classical communication system. Therefore, the gain is about approximately 10,000 times. So, which will highlight the importance of the semantic communication. So, the same thing for image communication. Image, let's assume image size is 512 by 512, 8 bits per pixel, and which is about approximately 2.1 million bits. And channel capacity, we assume 1 megabits per second. And then we can calculate the time required for transmitting this image is approximately 2.1 seconds. And for the semantic communication, goal-oriented semantic communication is considered here. We are only worried about 3 objects. So detecting 3 objects, for example, car, person, and the dog, use a semantic encoder to extract the object class and the bounding box like in YOLO. And each object needs 6 bits and 4 times 9 bits for the box coordinates, which is approximately about 42 bits, and multiplied by 3 because we have 3 objects, which is about 126 bits. Add some bits for the error protection, 130 in this case. As an example, basically we need about 250 bits or 256 bits altogether. So the transmission time, if we calculate that, we only need about 256 microseconds. So the gain is about 8,200 times compared to the classical communication, which again highlights the importance of the semantic communications. So this in mind, so the traditional communication system can be altered to accommodate the semantic communication system, and between the source and the source encoder, we have now embedded the semantic encoder, which extracts the semantic features, and then source encoding, channel coding, modulation, and channel demodulating, channel decoder, source decoder, semantic decoder, and the destination at the receiving station for entering the information. So now you can see that compared to the original block diagram, we have semantic encoder and semantic decoder, which also involve a lot of other complexities because the semantic meaning is not exactly same as the original information. Therefore, that in process involves the semantic noise, which can also be modeled based on the given media type and the given scenario. And semantic noise can also be modeled similar to how channel noise has been modeled in the past. So still, we are too early to come up with some kind of semantic noise modeling for different media types, image, video, and audio, and speech, and so on. So therefore, our objective is to model and improve the performance of the semantic channel such that the volume of data that needs to be transmitted in the technical channel is drastically reduced. So what is common knowledge? Common knowledge is beyond, it's not difficult thing, like it's beyond just knowing something. Simple knowledge is like, you know something, example, you know what a dog is. And shared knowledge, both the sender and the receiver knows the same thing. Example, we both know about what a dog is. And common knowledge is not only do we both know it, but also we also know that the others know it. And we know that they know, we know it, and so on. So it's a mutual knowledge of a shared context. For example, everybody knows about the rules of the chess if you can play chess. So therefore, that is considered as the shared knowledge between the players of the chess. So similar to that, there is a kind of a shared dictionary for meaning distribution between the traditional compared to traditional communication. The protocol is how to send this information. In semantic communication, the protocol is about what the bits mean between the transmitter and the receiver. So here, for example, I have listed some examples for semantic communication, shared knowledge at different applications. So, how it enables ultra-efficient communication without common knowledge. So, drone one must send raw sensor data, object at coordinates, and so on. Pixel color values are like this, and so on. So, there will be a lot of information involved in the traditional communication, which consuming high bandwidth and low meaning as well. With common knowledge, we can assume that the map is shared between the transmitter and the receiver. So, drone one can send a semantic message obstacle on the planned path and drawn to receive this message and instantly understand the meaning and implication because they share the same map as the goal. So ultra low bandwidth and high meaning, the message is just a key to unlock a complex data or idea stored in the common knowledge base. So next we consider technical implementation built in the shared foundation. Common knowledge isn't magic. It must be established and maintained. Pre-shared knowledge, how pre-loaded database agreed upon ontologies, standardized protocols. So use case IoT sensors in the factory, done in on the mission and so on. Co-learning and joint learning. So AI models, for example, neural networks at the sender and the receiver are trained together on the same data and the task. So therefore, the common knowledge can be updated or trained in real time. And result is that they develop aligned internal representation semantic language for concept. This is how many AI-based semantic encoders and decoders work. So dynamic updating is the other one, which is important for sharing the common knowledge. How the knowledge base is updated over time through interactions and new concepts are defined and shared when needed. And challenges it requires robust and secure negotiation protocol, which needs to be defined at the moment. So, what are the challenges with common knowledge? The fragility of the shared worldwide worldview. Establish how do you initially create and distribute the shared knowledge base across a massive network. Synchronization is the other problem. How do you ensure all devices have the same up-to-date version of the knowledge? And scalability is the other issue, that the knowledge base useful for drones is useless for smart kitchen and so on. And security is the biggest challenge at the moment. An attacker could poison the common knowledge to cause systematic failure or massive damage to the communication system. So the efficiency of semantic communication is directly proportional, therefore, to the breadth and the quality of the common knowledge shared between the agents, which will also be a critical factor for manipulating the virtual channel capacity. So exploiting common knowledge with AI because of the AI engine, so which it can basically generate some information at the receiver using the shared knowledge and some semantic features from the transmitter. So generative AI is the backbone of the semantic communication, like I told you before, with the help of the shared knowledge and the semantic features sent from the receiver transmitter. So the generative AI can be now be very powerful way of regenerating the information at the receiver, which is the foundation of the semantic communication. So basically, consider this one. Why send a 100 megabyte video stream of a parked car when a 1 KB message saying car is parked, status normal, which suffices the information to the receiver. So what is generative AI? It's like generating the information at the receiver with the help of common knowledge and the semantic features. For example, we can use diffusion model, GANs, and transformers and LLMs to regenerate the information at the receiver with the help of some semantic features from the transmitter and the common knowledge. So these are some of the applications of shared knowledge and generative AI solutions based on machine learning algorithms. So how it works, the new architecture, Gen AI powered semantic loop. We have semantic encoder, generate model, analyzes the raw data, it understands the context and extract the core meaning, and it sends some kind of semantic token to the receiver through the channel. The channel transmits the say small token, semantic tokens, not the raw data, highly efficient and robust to errors. And semantic decoder is another generative model intercepts interprets the semantic tokens using the same shared knowledge. It reasons about the intent and generates the required output. Example, text summary, a control command in an image. So it's a powerful use case, AI assistant on a weak link, saving the 99% of the bandwidth. Traditional method, for example, we consider 10 emails from my boss and summarize them. Your phone downloads all emails, which may be about 5 MB in this case, of data and process them. And then at the receiver, we have to consider and some actions based on the information that you received. So in GNAI powered semantic method, what it can do is it can download the emails and it semantically process them and then generate some kind of query, summarizes all these emails, and network sends about 200 byte query to the cloud. And in cloud, decode a powerful LLM executes the query on the stored emails and generates a summary. And then we only need about 2 KB summary data sent to the receiver. And the result is the user gets the same result thousands of times more efficiently than the traditional way of processing these email and communications. So the rise of communication systems, semantic communication systems, has been significant over the last few years. So before 2021, so there was not any papers on semantic communication or related technologies, but after 2021 and between 2021 and 2023, there was some increase in the research in this domain. But after 2023, over the last 2 years, you can see that there's a massive interest has been generated in semantic communication research with these numbers. So we can see that the number of patents filed in the last year, 2025, has been increased by 500%. So coming back to my last few slides in the presentation, the application of semantic communication can be in different domains. So here I have listed the main ones for high resolution video communication, omnidirectional video communication, extended reality applications, region of interest coding, scalable media coding, Internet of Things, machine-to-machine communication, narrowband video sensing, health applications, and space applications, agriculture, and there are a lot of areas that you can make use of this semantic communication for reducing the system network resources. So I have listed some of these applications, main applications in detail here, so you can go through it by yourself. So, but don't worry, this is only 10 different applications I have selected, but the applications will be much more higher than what I have listed here. For example, one of the critical application is the vehicle to everything communication system. You can see that if you use multiple cameras in a car, like in a busy street like this, there will be a massive amount of information needs to be sent to the controlling center to understand the context of the road and giving some commands to the automated cars. So that will involve huge amount of data rates and bandwidth and communication resources, where in this case, semantic communication can help you significantly better than the conventional communication system, because we don't know exactly the car in front of mine is a red one or a black one or a white one. So as long as the semantic information is sent to the control center, it can understand the activity of the road and then signal the other road users. So the one other critical application is the healthcare monitoring, especially for healthcare monitoring for dementia patients, which also I am working on that at the moment. So there will be a lot of application digital health monitoring as well. So with that, I conclude the presentation and thank you very much for your attention. And if anybody wants to communicate with me and cooperate with me on semantic communication or different aspects of media communication, please do contact me. My email address is here, and we are more than happy to welcome anybody who can collaborate with us for any of these research activities. Thank you very much, and goodbye from Glasgow in UK. Thank you very much.